Welcome to week 3, and in this week's video series we're going to be discussing parameterizations. But first I just wanted to connect this idea to what we have been discussing at least last week. The image that you see on the screen here is an image that we saw last week. We got introduced to CalcPlot 3D, and with that we were thinking about how to sketch surfaces in general, and to do that we discussed this idea of level sets and contour lines and all that sort of stuff. And so now we are going to think about, well, if we have a surface and we're looking at a certain path on the surface, and we could think of that path as a level set for all intents and purposes, we want to be able to describe that path, and that's where parametrization comes into play. In your summer homework, I know you worked a little bit with parameterizations. We've seen parameterizations a little bit, and you might even recall some of these things that we're going to be discussing from Calc 2. And then actually in our very first class, we actually introduced some parameterizations, change of coordinates, cylindrical coordinates and spherical coordinates. Okay, so we're just going to expand on that today. And really, when I use that language of a parameterized curve, really it's just a vector representation of a curve that's multidimensional. So we can talk about a curve in 2D. You can see here this parabola. It's not a function, at least in x, but we can see that if we parameterize it with another value t, and that's called our parameter, and change the value of t, we can actually, if we do a good job, have t trace along the curve, and that's what we're going to call a path. So really what we're going to focus today is get a lot of practice, because this is one essential skill for all of Calc 3. We need to be very good with parameterizations. And then, since it is calculus, right? Calculus is the study of rate of change. We want to think about the rate of change with these parameterizations. Okay? So let's start off with an example here. So it's just a line. 3x plus 2y is equal to 22. All right? And we want to just find the parameterization of this line. To start finding a parameterization, it would probably be useful to just have a little sketch in the back of our minds, or on paper. So if I draw just a quick little sketch, okay, here are my axes, x and y, and this is just going to be a sketch, so not to scale or anything, but when I draw it, the sketch of the line should look something like this, roughly. And again, imagine it's straight and all that stuff. But if we want to think about a parameter, introducing a parameter, maybe we want to use t as a parameter, we need to figure out how to insert this. Now, one strategy that you have employed in past problems, and you might need to go digging through your materials to refresh your brain on this, but if we want an equation in one parameter, we want to try and eliminate the other. So what we can do is take our original equation and maybe isolate a variable. And it's actually going to be easy to isolate y here. So if you isolate y, I believe you get 11 minus 3 halves x. And then with this, we have now represented y as a function of x. And what we can do with this is actually say, well, let x equal t. And then in terms of a vector representation, we can say that this is the parameterization here is going to be t, comma, 11 minus 3 halves t, not x, because x is now t. Let's erase that. Okay, and again, this would go from xy to that, and to generate the entire line, a parameterization needs not only kind of a vector representation, but you need a restriction. So t is a real number. So a parameterization, you need the two things. So that's fine and well. And actually, since it is a vector, I should put it in angle brackets. So let's do that. All right. So that is one parameterization. Let's see if we can find another. Okay. I'm going to tell you that we have 2 points on the line. I'm going to say this is point A, and this is the point 2, 8, and that's an XY coordinates. And there's another point B, which is the point 6, 2. Okay. We might remember from Calculus 2, towards the beginning or towards the end of the first semester, that we can really think of a line as a point plus some multiple of the slope. Okay, well, if we do that, we can say, well, this line should be the point to 8, and remember, Stuart kind of has this discussion about the difference between point and vectors and all that stuff. We're not going to be so concerned with that discussion here. But then a multiple of a slope, I can represent that as t, our parameter, and then the slope would be the vector that is between a and b, and I'm going to call that vector, okay, so from a to b, this is going to be the vector u, and so if I write that here, it's going to be t times vector u, and so then I get the vector 2, 8 plus t, and then to find that vector u, the x coordinate is going to be the difference in the x's, so 6 minus 2, and then the y is going to be a difference in the y's, 2 minus 8, okay, and so then I get 2, 8 plus t 4 minus 6, so that form is fine. Otherwise, if you just wanted an xy, it can be 2 plus 4t, 8 minus 6t. And that should be another vector representation of the line, but again, I have a vector representation and I need restrictions on the parameter, so t actually here is going to be with an r. Okay, now this is great. So we have 2 different representations of the line. Either one is perfectly fine, and this is just using our prior knowledge. Okay, if we want to check that this is indeed the case, that both of these are correct, we can go into GeoGebra, and what I did in the upper left hand corner, you might see, is that I just typed in that original function, and then I made a slider using the option up here, and I also placed the points A and B on this line. Okay, and then what I did was for the first parameterization, I started at the y-intercept, so that was at the 0, 11, and from there I think you can just drag the slider and see, yeah, this is going to progress along the line at a different rate as compared to the second parameterization that we found. So if I now show the second parameterization and not the first, I can again drag my slider, and it's going to move a little bit quicker just because the quote-unquote slope, or the vector representing the direction, was a little different. So both parameterizations move across the line, just at different rates. And so that's going to be the end of this video. We're going to continue working through some examples in future videos.